Assalamualaikum and very good day. I'm Dr. Hidayah from the School of Civil Engineering, Faculty of Engineering, University Technology Malaysia. First, I would like to welcome everyone to my lecture video. This video is for online learning for the course of Advanced Road Material. In this video, I will discuss on the concept of nanomaterials for road application. So stay with me. I hope this video will benefit you and others. Okay, so let's have a look on what I have prepared for you. Okay. This is table of contents. The topic that we're going to discuss today, the first one we're going to have a look on some introduction about the nanomaterials and nanotechnology, and then measurement techniques for nanoparticles, nanomaterials in asphalt mixture, and finally on nanomaterials in concrete. Okay, first, let's have a look on the overview of nanotechnology. Nanotechnology is science, engineering and technology conducted at the nanoscale, which is about 1 to 100 nanometers. It is a branch of technology that involves an application of extremely small things and can be used across all the other science fields such as chemistry, biology, physics, material science and engineering. Compared to the previous works before the year 2000, most of the studies focus on the macro and micro research, and after 2000, the nanoscience has become significant in solving the industrial problem. Nanoscience and nanotechnology involve the ability to see and to control individual atoms and molecules. Everything on Earth is made of atoms. The food we eat, the clothes that we wear, the buildings and houses that we live in, and even our own bodies. But something as small as an atom is impossible to see with the naked eye, and therefore many more technologies are discovered for better understanding of the nanomaterials. Okay, let's have a look on the application of nanotechnology. The year 2000s have seen the beginning of the applications of nanotechnology in commercial products, and most applications are limited to the bulk use of passive nanomaterials. Currently, the major application is related to the following products. For examples, include titanium dioxide in sunscreen, cosmetics and some food products, silver nanoparticles in food packaging, clothing, disinfectants and household appliances, such as carbon nanotube for stain-resistant textiles, and cerium oxide as a fuel catalyst. Other major applications are also significant in the field of electronics and paints, such as nanocoating and nanocomposite. And then, there are many more applications in other fields. Nanotechnology is also being applied or developed for a variety of industrial and purification processes. Purification and environmental cleanup applications include the water filtration, wastewater treatment, and groundwater treatment. In construction industry, the applications may include construction materials such as for steel fabrication, in glass, surface coatings as well as for fire protection and detection. So basically, what is nano? The word nano is used to indicate 1 billionth of a meter or 10 to the power of minus 9, and a world of things is built up from the tiny scale of nanometers. Nanoparticles or nanomaterials in principle refer to a material particle that having dimensions and tolerance of less than 100 nanometers or between 1 and 100 nanometers, especially the manipulation of individual atoms and molecules. This concept of nano is taking the advantage of the particle's characteristics, which are very small in size. It's lighter, where the particles can move faster, and also high specific surface area of the material, that making it become more reactive than the materials at micro size or macro size. Based on this slide, the figure compares different things with various sizes in nanoscale, from the size of baseball at 1000 million nano to bacteria size of 1000 nanometer. And of course, these are not considered as nanoparticles yet. Like what I've mentioned just now, nanoparticles or nanomaterials are considered at the size of less than 100 nanometer, as shown in the figures such as the virus, protein or DNA, glucose, and finally the water molecules. Well, the closest example is water. The water is an example of nanoassemblies of molecules where the size of the water molecules is within the nanoscale, which made of oxygen and hydrogen. Okay, now let's have a look on various terms related to nanomaterial study. First is the quantum mechanics, or sometimes it's called quantum physics. These terms can be referred to a subset of physics explaining the physical or mechanical behaviors at the molecular and atomic level. Others is that any materials studied at the nanoscale level will normally be considered as ultra small or superfine materials. So meaning that when we talk about nanoscience or nanotechnology, it's about the study of materials at nanoscale which involve the design, fabrication, and application of nanostructures or nanomaterials. And this study requires advanced imaging technique for investigating the material's behavior and producing very fine powders with the particle size between 1 to 100 nanometers. Furthermore, the study also covers the fundamental understanding on the relationships between physical properties and material dimension. Next is the nanomaterials. So how can we define the nanomaterials? This is not new undiscovered material. It can be produced from any types of normal materials but are very small in size. Like what I have mentioned earlier, at least one external dimension in the size range of 1 to 100 nanometers. So due to their small size, the properties are no longer the same as when they are in a big size. And they can be either organic or inorganic. For example, metal, polymer, electronic, ceramic, and composite. Today, scientists and engineers are finding many ways to produce materials at the nanoscale. This is to take advantage of their enhanced properties such as higher strength, lighter weight, increased control of light spectrum, and greater chemical reactivity than their larger scale counterparts. The unique properties of nanomaterials have led to their use in many applications in industrial and non-industrial sectors like aerospace, construction, energy, textile, automotive industry, transport, and medical technology. A few examples of application are presented in the table, as you can see here, such as carbon nanotubes, titanium oxide and dioxide, platinum, iron silica, nano clay, silver and gold, and graphene. Okay, next we have a look on classification of nanomaterials. In general, it can be identified according to their dimension and morphology, which is their form and shape. Nanomaterials can be classified as, first one is zero-dimensional, such as spheres and clusters, and then one-dimensional, such as nanofibers, and then next two-dimensional, such as films, plates, and networks, and then finally three-dimensional, which can be in many forms. Okay, let's have a look on the details of the classification. This slide shows the details of various dimensional of nanomaterials. First, like I said earlier, we have zero-dimensional, which refers to a nanoparticle with all dimensions are in nanoscale, which is less than 100 nanometer. It's like one dot. And then we have a one-dimensional where at least two dimensions are in nanoscale, such as nanotubes and nanowires. This refers to the cross-section of the nanotubes, for example, as you can see from the image provided, which means the length of the nanotube is not in nanoscale, but the cross-section, okay, the cross-section. And then we have two-dimensional that has one dimension in nanoscale, which is, for example, the film thickness, okay. The film thickness less than 100 nanometer, but the grains are not in nano size. It's microcrystalline. Okay, the applications such as, for example, we have nano coating, nano laminates, and nanofilms. Okay, so meaning that all the dimension of the film or nanofilm is not in nanoscale, but only the thickness. So meaning that only one dimension of the thickness of the film in nanoscale. Okay, next we have three-dimensional of nanomaterials. So this time, the film has thickness of more than 100 nanometers, but contains of grains with dimension in nanoscale or nanocrystalline, such as the nanocomposite. So it can be in various form, whether it can be made of glass or metal, or any other relevant material. Later, we're going to discuss on different types of nanomaterials used in asphalt mixture and also in concrete. Okay, next, why materials at the nanoscale can have different properties? This is because it depends more on surface area than the particle composition. So due to their small dimensions, nanomaterials have extremely large surface area to volume ratio, which makes a large to be the surface or interfacial atoms, which results in more surface-dependent materials properties, especially when the size of nanomaterials are comparable to length. The entire material will be affected by the surface properties of nanomaterials. This, in turn, may enhance or modify the properties of the bulk materials. The high surface-to-volume ratio introduces many size-dependent phenomena that lead to greater chemical reactivity and mechanical properties such as strength. An increased surface area-to-volume ratio also means increased exposure to the environment. The surface area-to-volume ratio for a material or substance made of nanoparticles has a significant effect on the properties of the material. Firstly, materials made up of nanoparticles have larger surface area when compared to the same volume of material made of bigger particles. For example, let us consider a cube as shown in the slide. The surface area of a cube is 6 with a volume of 1. Therefore, the surface area to the volume ratio will be 6. But as the size of the cube increases, the surface to volume ratio also will decrease. It also means that when a given volume of material is made up of smaller particles, the surface area of the materials increases. Therefore, as the particle size decreases, a greater proportion of the particles are found at the surface of the material. For materials made of nanoparticles, they have a much greater surface area per unit volume ratio compared with the materials made up of bigger particles. This leads to nanoparticles being more reactive, as chemical reactions occur between particles that are on the surface. A given mass of nanomaterial will be much more reactive than the same mass of material made up of large particles. Okay, next we have a look on synthesis of nanomaterials. There are two components of the synthesis for the nanomaterials. First is to make or to produce the nanomaterials, which involve the process of two major processes. First one is top-down, and another one is bottom-up. And then second is to characterize the size-induced properties or performance. For example, in various chemical compounds such as metal or elements such as carbon and oxide. And also the morphology and structure of the materials. Okay, next we have a look on how to create nanomaterials. There are many different ways of creating nanostructures, and of course, macromolecules or nanoparticles and so on can be synthesized artificially. for certain specific material. Using these methods, synthesized materials can be arranged into useful shapes so that finally the material can be applied to a certain application. This slide shows the schematic illustration of the preparative methods of nanoparticles. These indeed allow us to think in both the bottom-up or the top-down approaches in order to synthesize nanomaterials. It's either to assemble atoms together like the sol gel process, or to disassemble or break the bulk solid into finer pieces such as through mechanical grinding until they are having only a few atoms. The first figure shows the schematic representation of the principle of mechanical milling. This is a typical example of top-down method of nanomaterial synthesis, where the material is prepared not by a cluster assembly but by the structural decomposition of coarser-grained structures as the result of severe plastic deformation. This has become a popular method to make nanomaterials because of its simplicity. Other benefit is that the equipment needed is not expensive and then it's applicable to different classes of materials. However, there are concerns about this method, such as the contamination of the milling process. In fact, the contamination problem is often given as a reason to dismiss the method, at least for some materials. Mechanical milling is typically achieved using high-energy shaker or mills. The energy transferred to the powder from the steel balls depends on the rotational speed, size and number of the balls, ratio of the ball to the powder mass, and the time of milling. So nanoparticles are produced by the shear action during grinding. The second figure shows the schematic representation of sol gel process of synthesis of nanomaterials. Sol gel method of synthesizing nanomaterials is very popular amongst chemists and widely employed to prepare oxide materials. In materials science, the sol gel process is a method for producing solid materials from small molecules. This process is a wet chemical technique that uses a chemical solution to produce an integrated network or gel. They undergo hydrolysis and polycondensation reactions to form a system composed of nanoparticles dispersed in a solvent. So after creating the nanomaterials, they also can be characterized in terms of physical properties such as the area and shape. And then chemical properties such as the reaction and compounds and also elements. And then their structural properties in terms of mechanical properties, particularly the strength. Okay, like what I have mentioned previously, nanotechnology has been used in various fields, including civil engineering works. Here are some of the unique properties provided by having the nanomaterials in the structures, such as it will provide lighter and stronger composite, work as fire insulator, which refers to the reduction in thermal transfer rate, and then sound absorber, and water repellents or waterproofing, and finally, to provide better cementitious materials. Okay, next, let's have a look on measurement techniques for nanoparticles. There are various techniques for detecting, measuring, and characterizing nanoparticles. There is not a method that can be selected that is the best method, but rather a method is chosen to balance the restriction of the type of sample, the information required, time constraint, and the cost of the analysis. A straightforward technique may simply detect the presence of nanoparticles. Others may give the quantity, the size distribution, or the surface area of the nanoparticles. These measurement techniques differ from characterization techniques for assessing the chemical content of a nanoparticle sample, the reaction on the surface of the nanoparticles, or for the interaction with other chemicals present. And sometimes, measurement techniques will be combined to provide more information from one sample. So basically, the properties of nanoparticles are size-dependent and it can be expressed in linear dimension characteristic derived from its shape. There are two basic concepts of the measurements. First is by taking the actual measurements of the dimension using microscopic techniques. For example, the measurement of many dimensional parameters from the particle image. Second is by considering the relationship between particle behavior and its size, such as using dry powders dispersed in suspension. So different techniques will suit different types of samples. For example, some techniques require the use of a suspension or liquid samples. There are techniques for in situ measurements of samples and others that require treatment of the sample before analysis. Sometimes samples may not be able to withstand the required treatment and decompose or react. The amount of sample required can also vary and restrict choice of the technique. This slide shows the different measurement techniques such as field emission scanning electron microscope, FESAM or SEM, and then high resolution transmission electron microscopy, TEM or HRTEM, and then PCS, surface area analysis, and XRD. Since different techniques provide different information, efforts have been made to standardize the way nanoparticles are measured. This is to assess the risk of exposure to human health and environmental. The details of the technique will be discussed in the next slide. First, let's start with the microscopy method. These three methods are normally used to determine the nanoparticle size and characterization. The first is scanning electron microscopy or FESAM, field emission scanning electron microscopy. This method uses a high energy electron beam and the beam is scanned over the surface. The sample must be under a vacuum and electrically conductive at the surface. This can be achieved by having a coating on a non-conductive sample. This requirement can be restrictive, and again, this technique can be time-consuming and expensive. Then, the transmission electron microscopy. These techniques combine the ideas of looking at the surface of the sample and into the sample with an electron beam. It uses an electron beam to interact with a sample to form an image. The sample preparation can be difficult as a thin sample must be prepared, and the process can be time-consuming and costly. So another version of TEM is HRTEM or High Resolution Transmission Electron Microscopy. This gives a higher resolution which is beneficial when studying nanoscale sample. However, it does require understanding of the sample to allow better description of the results. Next is the atomic force microscopy or AFM. It's a form of scanning probe microscopy. It uses a mechanical probe to feel the surface of a sample. This can offer a 3D visualization for air sample or liquid dispersion. This technique requires less cost and time than the TEM or SEM. However, based on previous application of these three microscopy methods, there are criticisms related to the measurement of nanoparticles. The criticism is mainly due to the difficulties in preparing the sample for scanning, while others on the resolution of crystalline samples and whether individual crystal particles are correctly identified and the need for a representative samples to be chosen for the study. A small sample is chosen to be viewed, and this may not be an average of the sample as a whole. Next are the PCS, Differential Mobility Analyzer, and CPC. These methods are normally used to determine the particle size distribution, and concentration of particles. Let's start with PCS. PCS measures the scattering pattern produced or intensity of the scattered light when the light is shown through a sample. This will give the radius of a sample and therefore an estimation of the average particle size and distribution of particles through the sample. The sample must be a liquid, solution, or suspension. It must also be very dilute or the scattering of the light can be unclear. The technique is sensitive to impurities and the viscosity of the sample must be known. Next is a DMA. This technique will classify charged particles according to their mobility in electric field. An aerosol sample is charged and sent in airflow into a chamber where electric field can be applied. The rate at which the particles migrate to the end of the chamber will depend on their electrical mobility. Particles with the same electrical mobility will be the same size, and then sorted into different sizes and the size distribution. Next is the CPC. A CPC uses a condensation technique to enlarge small particles, such as nanoparticles, to a size that can be easier detected by an optical detector. This is to determine the concentration of particles in a sample. The technique is suitable for aerosol samples and higher temperature sample, which can be up to 200 degrees Celsius. Okay, next we have a look on NTA, Nanoparticle Tracking Analysis, XRD, and APM, Aerosol Particle Mass Analyzer. These methods are normally used to determine the particle size distribution, and particle mass. The first one, NTA, is a technique that provides information of particle size distribution, and a real-time view of the nanoparticles in a sample. The sample must be a suspension for which a wide range of solvent can be used. A laser light is used to directly visualize the nanoparticles through an optical microscope. A digital camera is also used to record the observed particles. Software can then produce a frequency size distribution graph. NTA could be combined with techniques such as PCS to maximize the information and accuracy of the measured parameters. And then XRD, X-ray diffraction, which can be used to look at single crystal or polycrystalline materials. A beam of X-rays is sent into the sample, and the way the beam is scattered by the atoms in the path of the X-ray is studied. The use of XRD is often compared to the microscopy methods. XRD avoids issues of representative samples and determining crystals as opposed to particles. However, XRD can be time-consuming and requires a large volume of sample. Okay, next, the APM. APM is the only technique listed here that concentrates on the mass of the nanoparticles. It is a technique independent of particle size, shape, orientation, or the properties of the gas surrounding the particles. It classifies particles based on their mass to charge ratio. So, among all the methods presented here, how to consider which method that should be selected for your work? Here I have listed a few considerations in the method selection. First, you have to be clear of what exactly the aim of the measurement, whether your concern is on the number, mass, particle size, or surface area. Then, what type of sample is required for the analysis, whether it's in suspension, solid, or liquid. Okay, and then, does the technique requires the sample to have a certain properties or be prepared in a certain way? And then, what exactly the amount of sample required, and will the sample be destroyed? This is like destructive or non-destructive. And how long the analysis, and what are the costs involved in the measurement technique. Therefore, it should be noted that the right selection of the method determines the final quality of the results. Okay, next, let's have a look on the various types of nanomaterials used in asphalt mixtures. In pavement engineering research, nanotechnology is used as a form of new materials or device and system at the molecular level. A number of researchers have used nanomaterials in Portland cement materials. However, nanomaterial used in asphalt pavement started a bit late. In recent years, some researchers have started to work on the improvement of asphalt materials with nanomaterials in asphalt cement and emulsion. Although bitumen material such as asphalt are mainly used on a large scale and in large quantities for road construction, the macroscopic mechanical behavior of these materials still largely depends on the microstructure and physical properties of the micro. Although researchers, material manufacturers, and engineers have explored this potential for many years, the use of nanotechnology has been limited. New efforts are taken to develop nanomaterials for pavement application that will improve the mechanical and physical properties of the nanoscale, as well as the durability of this important group of building materials. Therefore, nanotechnology enables the design of systems with high performance density, high sensitivity, surface-specific effect, large surface area, high pressure, resistance, and catalytic effects. All properties are directly or indirectly derived from the small size of the nanoparticles. There are various nanomaterials which have potential to be used in asphalt modification, such as nano clay, nanosilica, nanohydrated lime, nanofibers, and nanotubes. A few examples of some related research works are provided in the next slide. This section addresses specific applications of nanotechnology in the field of road asphalt. There are a number of areas where the use of wise technology techniques can improve the durability and performance of the asphalt, which include the advanced and intelligent materials used for paving. A number of studies have been performed on nanoparticles in the asphalt coating industry. Nanotechnology is predicted to provide great potential for the development of the asphalt coating industry in materials design, manufacturing, properties, testing, and monitoring. Some of the studies perform molecular simulations to evaluate the self-repair of asphalt cracking in asphalt mixture. So, it can be said that nanotechnology has various applications in the asphalt industry, including asphalt surface protection against sunlight, waterproof and freezing coating of asphalt surface, making a non-stick surface for easier control of an asphalt mix steam, provide better addition between two layers of asphalt or between asphalt layer to non-asphalt layer, and then cavity and cracks control. And some of the nanomaterials also used as a rejuvenating substance for aging problem. Researchers have used nanomaterials modified asphalt and characterized the properties such as dynamic modulus, creep, fatigue, and rutting. For example, in this figure, the rutting depth measured using asphalt pavement analyzer (APA) illustrated that the addition of 2 to 4% nanomaterials by weight of asphalt can reduce the rutting depth by almost half. Furthermore, it was found that the rut depth of nanomaterials modified asphalt mixtures decreased compared to the control mixture, and smaller rutting depth was observed for a greater percentage of nanomaterials in mixtures. This shows a potential improvement in the properties of asphalt mixture. Okay, next, let's have a look on various types of nanomaterials used in asphalt mixture. Let's start with nano clay as a modifier of asphalt. So what is nano clay? Nano clay is nanoparticles of layered mineral. It's a modified clay, and based on previous study, it has potential to reinforce and modify asphalt binder, and also was found compatible with asphalt and polymer. Here are some benefits of the nano clay modified over the conventional asphalt binder. Previous study has found that the addition of nano clay in asphalt binder has improved short and long-term aging resistance. And then it also has a potential to enhance various properties such as stiffness and tensile strength, tensile modulus, flexural strength, and thermal stability. In other study, they have found that nano clay can provide higher rutting resistance compared to the conventional asphalt binder. The research on asphalt binder shows that a small percent of nano clay in the mixture may significantly improve the performance of asphalt materials. For example, in some research work, it was found that 2% of nano clay in the asphalt binder may increase the shear complex modulus almost 2 times of the conventional asphalt binder. This indicates the massive improvement in the rotting resistance of asphalt. Others, nano clay is also used to improve the modulus and tensile strength, flame resistance, and structural properties. Nano clay is widely used in modification of polymer to improve the mechanical and thermal properties. One of the most frequently used of nano clay is MMT. Other classes such as bentonite and kaolin and a few others depending on chemical composition and morphology. This is an example of nanoclay particles which kind of similar to mudstone. Here I would like to share some results on nanoclay in asphalt. The first graph shows the result of tensile strength and the second graph shows the results of flexural strength. The addition of nanoclay from 1% to 5% has been compared to the conventional of asphalt binder. So from the graph, it can be seen that the flexural and tensile strength increases at a constant rate by adding nanoclay. At a certain stage, it starts to decrease, which suggests that an optimum content of the nanoclay in asphalt. Next, we have the results of penetration and softening point. Two types of nanoclay were compared with unmodified binder, with the addition of nanoclay content 2%, 4%, and 7% by weight of the binder. Overall, it shows that the addition of nanoclay hardened the asphalt binder and increased softening point, which shows that it can stand at higher temperature before start to flow. Next is the results of the previous study in terms of ductility and modulus. From the results, it shows that the addition of the nanoclay seems to reduce the ductility of the asphalt binder and improve the modulus of the binder with the increase in nanoclay content and temperature of the testing compared to the conventional or unmodified binder. Next, let's have a look on carbon nanotubes. These nanomaterials are made of carbon with diameters found to be as low as 0.4 nanometers. It possesses unique mechanical properties with remarkable electrical and thermal conductivity and exceptional tensile strength because of their nanostructure and strength between carbon atoms. By adding sufficiently high percentage or more than 1% to the base bitumen, it affects the rheological properties. So by using carbon nanotubes in asphalt pavement, it can provide better rotting resistance. And it was mentioned that by using carbon nanotubes of 0.1% of the asphalt binder will decrease the thickness of the root layers and reduce materials consumption. Others provide resistance to thermal cracking. And also the addition of nanotubes has the potential to reduce susceptibility to oxidative aging for long-term performance. This slide shows the image of carbon nanotubes and illustration of a single-wall carbon nanotubes. Next is the nanosilica. This type of nanomaterials is a versatile compound on Earth that is mainly used in industries for the production of silica gels, foam silica, and many more. Silica nanoparticles have been used in the industry to reinforce elastomers as a rheological solution. Silica nanocomposites have also received scientific attention. The advantage of this nanomaterial lies in their low production cost and high performance characteristic. The main characteristic of nanosilica is its ability to absorb moisture, and that's why in many applications, this material is used to control local humidity. By adding nanosilica to the base asphalt adhesive, decrease slightly the viscosity values of the asphalt binder. The low viscosity of the asphalt binder indicates that a lower compaction temperature or lower energy consumption can be achieved during the production process. Adding nanosilica to the asphalt was found to improve the recovery ability of the asphalt, stress properties and relaxation capacity of the asphalt. Others, the nanosilica also enhanced the anti-aging performance, fatigue cracking and anti-stripping. This slide shows the micro images of nanosilica and its dispersal status in a given asphalt matrix. From the image, the nanosilica seems to well dispersed in the asphalt. Next is the organosilicon or zircosol. This organosilicon compound contains carbon and silicon. Most organosilicon compounds are similar to the ordinary organic compounds, being colorless, flammable, hydrophobic, and stable in air. Zircosol molecule, when dissolved in solvent, has estimated size of 3 to 6 nanometers. These types of product provide water repellents by modifying surface characteristic from hydrophilic to hydrophobic. In other words, it provides a waterproofing mechanism to the materials. This will provide waterproofing layer on all types of soil, aggregates, and other inorganic road construction materials and reduce the moisture susceptibility of hot mix asphalt. Other benefit is that in terms of providing better UV and thermal resistance. This nanomaterial is new generation of nanotechnology which has been developed for waterproofing, UV and thermal resistance due to its nano size and penetrative power. Water intrusion in building materials has been a problem for the last 1,000 years. These eco-friendly organosilicon products that can render most materials hydrophobic for cycles of 20 to 30 years at a very economical cost. So how's the performance of these nanomaterials with asphalt mixture? So based on the previous study, the use of this material in asphalt mixture containing limestone and granite increases the tensile strength between 3% to 14% respectively compared to the control sample. And then aggregate coverage with this material decreases the air voids in asphalt mixture and increases the binding capacity. And finally, this product provide a formation of hydrophobic nanolayers on aggregates, which can lead to the increase of fatigue life. So, the advantages of using nanomaterials in modified asphalt are widely recognized for self-healing properties, such as the use of induction, heating, and rejuvenation. And then, to improve the storage stability, especially in polymer-modified asphalt. And then, it has the potential to increase the resistance to UV, which related to the aging problem. In certain application in asphalt, the nanomaterial has the potential to reduce the moisture susceptibility underwater, improve the properties of asphalt mixture at low and high temperature, which reflect the cracking and rutting potential, and then improve the durability of asphalt pavement, decrease maintenance requirements, and finally, save the energy and cost when the evaluation is made based on the life cycle or cost-benefit ratio. These improvements in performance, durability, and life cycle cost saving compared to the unmodified pavements have led the widespread use of the nanomaterials in modified asphalt pavement. Okay, next we have a look on different types of nanomaterials used in concrete. So concrete is a mixture of ordinary Portland cement, OPC, fillers such as sand, coarse aggregate, admixtures, and water. Concrete durability becomes a very important factor, especially when concrete is exposed to varying climatic conditions. Therefore, a number of ways to improve its service life, and one of them is through the use of nanoparticles as supplementary cementitious material in concrete, which has led to improved permeability and strength of the concrete. As the material properties differ significantly at the nanoscale than a larger scale, the properties possessed by the concrete containing these particles also vary differently. In terms of the mechanical properties, first, it provides better or higher strength, and then better rate of hydration, which refers to the hardening process, and then decrease in porosity, preventing crack initiation, which is through crack arrest and interlocking effects provided by nanoparticles, which improve the toughness, shear, tensile, and flexural strength of cement-based materials. Then, it has the potential to provide better durability against weather, temperature, and moisture. And also the use of nanomaterial in concrete provide new surface properties such as the photocatalytic surfaces, which act as decontamination and decomposition agent, which provide self-cleaning surfaces and water-repellent surfaces. This is the list of potential nanomaterials used in concrete, such as carbon nanotubes, CNT, carbon nanofibers, CNF, nanosilica, and titanium dioxide. First, let's have a look on nanosilica. Many researchers have attempted to improve the behavior of cementitious matrix by adding nanosilica in concrete. The nanosilica in concrete or mortar will increase the density, reduce porosity, and improve the bonding between cement matrix and aggregates with higher compressive and flexural strength. The compressive strength evaluation of cement mortar with nanosilica was discussed for different water-cement ratio, and from the experimental results, it is confirmed that the compressive strength of mortars with nanosilica were higher than conventional at 7 and 28 days. It was found that the nanosilica behaves not only as a filler to improve the microstructure, but also as an activator to promote pozzolanic reactions and superplasticizer that plays important role during mixing the cement with nanoparticles. The pozzolanic reaction is a chemical reaction that occurs in Portland cement upon the addition of pozzolans, which in this case, the nanosilica, with the presence of water. The process provides a good cementitious properties in concrete and improve the cement hydration during the hardening process. This figure shows the results of compressive strength of a concrete tested at various sizes of silica from micro size to nano size, including conventional concrete. Based on the plots, it can be seen that the finer the size of the silica added to the concrete, the better the compressive strength. This is possibly due to the high surface area that could cause the nanosilica particles become more reactive and improve the properties of the concrete. Next is the carbon nanotubes. This material acts as nano reinforcements in cement-based materials. They provide extraordinary strength with a very high modulus of elasticity and tensile strength, and they also have unique electronic and chemical properties. That's why, when researchers think of nanomaterials reinforcement in concrete, carbon nanotubes come as the first option. There are two types of carbon nanotubes. The first one is single-wall carbon nanotubes. Second is multi-wall carbon nanotubes, as illustrated in the slide. The addition of CNT to concrete can significantly enhance some mechanical as well as physical properties of the material. The use of carbon nanotubes increases the strength and durability of cementitious composites, as well as for pollution reduction. CNT in concrete also help to control the crack propagation, and it has been proved that there is a good interaction between CNTs and cement faces, indicating the potential for crack bridging and enhanced stress transfer. And then we have nanotitanium dioxide. It is another material which has gained popularity for its usage in concrete studies in recent times. Similar to investigation on nanosilica in cementitious matrix, many researchers have discussed the possible methodologies and observed advantages by using nanotitanium dioxide in cement matrix, especially to achieve high mechanical properties such as compressive and flexural strength, and the most interesting properties, which refers to the photocatalytic effect. This material acts as the nanoparticles that fill the nanovoids in concrete, which leads to the increment of compressive strength. These nanoparticles accelerate and increase the degree of hydration. Its photocatalytic properties have been used to remove mainly organic pollutants from the surfaces directly exposed to UV radiations, such as pavements and cement-based finishing products, which make it as self-cleaning product. The use of titanium dioxide photocatalyst in combination with cementitious and other construction materials has shown a good effect in the removal of nitrogen oxide. Through the explanation on nanomaterial, I think I have mentioned few times of photocatalytic effect. So what exactly this effect, or other term, is photocatalytic oxidation? This condition involves the decomposition of pollutants by UV radiation. For example, in the figure, the photocatalytic concrete exposed to the UV radiation will create hydroxyl radicals, which are highly reactive electrons. These electrons aggressively combine with other elements in the air, such as bacteria and harmful pollutants. Then the chemical reaction takes place and effectively oxidizing or burning the pollutants, which later breaks the pollutant down into harmless carbon dioxide and water molecules. Then, as the water flows off the surfaces, it removes pollutants effectively. This concept is used in Japan to keep the paving clean and to reduce the effect of air pollution. Next, let's have a look on these advantages of nanomaterials. First, in terms of instability of the particles, retaining the active metal nanoparticles is highly challenging as the kinetic associated with the nanomaterials is rapid. In order to retain nanosize of particles, they are encapsulated in some other matrix which are prone to attack and transformation. These include poor corrosion resistance, high solubility, and phase change of nanomaterials. Next is the fine metal particles that can act as strong explosive due to their high surface area coming in direct contact with oxygen. Their exothermic combustion can easily cause explosion. And then in terms of impurity, because nanoparticles are highly reactive, they interact with impurities as well. In addition, encapsulation of nanoparticles becomes necessary when they are synthesized in a chemical solution. And then biologically harmful. Nanomaterials are usually considered harmful as they become transparent to the cell. Toxicity of nanomaterials also appears predominant due to their high surface area and enhanced surface activity. The interaction with liver or blood could also prove to be harmful. And then, difficulty in synthesis, isolation, and application. It is extremely hard to retain the size of nanoparticles once they are synthesized in a solution. Therefore, the nanomaterials have to be encapsulated in a bigger and stable molecule or material. Free nanoparticles are hard to be utilized in isolation, and they have to be interacted for intended use via secondary means of exposure. During processing, the finer particles tend to merge and become bigger and stable at high temperatures and time of processing, which this can cause it to be very expensive. And finally, on the recycling and disposal, there are no hard and fast safe disposal policies evolved for nanomaterials. issues of their toxicity are still under question, and results of exposure experiments are not available. Hence, the uncertainty associated with effects of nanomaterials is yet to be assessed in order to develop their disposal policies. Before I end my lecture, I just want to highlight a little bit more on potential hazards of nanomaterials. There are concerns about the use of nanomaterials for the safety of the environments and humans. This concern should be specifically addressed in the road pavement application. In 2004, the Royal Society and the Royal Academy of Engineering published a major review of the opportunities and uncertainties of nanotechnologies. This was one of the first reports to highlight the potential risks to health and environment that may arise from exposure to nanomaterials. Following significant research in this area, there is now a substantial evidence indicating considerable differences in hazard between nanomaterials and their bulk counterparts, and also between different types of nanoparticles. So, potential issues for nanomaterials which should be kept in mind when handling and using nanomaterials include: first, in terms of reactivity, the surface charge may play a significant role, and nanomaterials can possess a significant proportion of reactive metals. For example, the residual catalyst from the manufacturing process, which may possess hazardous properties. In addition, photocatalytic nanomaterials may also cause inflammation and oxidative damage. Next, in terms of solubility, some types of nanoparticles become more soluble as particle size decreases. This could imply increased bioavailability of ions from particles previously considered to be insoluble. Next is the morphology. Based on toxicological research on industrial fibers, the fibers with a diameter less than 3 micrometer are considered to be hazardous to human health. Some high aspect ratio nanomaterials such as carbon nanotubes and nanowires meet this requirement. Then, specific surface area. One of the main reasons nanomaterials tend to be more reactive than their corresponding larger scale equivalents is that, per unit mass, they have a much higher surface area. And finally, translocation potential. As a result of their small size, nanoparticles and other nano-objects can reach parts of biological systems which are not normally accessible by other larger particles. Therefore, proper precaution and information regarding handling on the nanomaterials should also be studied and taken into consideration for future research and application. In addition to what we have discussed previously, it shall be noted that a number of issues on using nanomaterials for asphalt and concrete pavements need to be further understood. The study is still in its very early stages, with more aspects of mechanical, physiochemical and morphological characterization of nano-modified asphalt and concrete mixtures to be considered in the future. Okay, that's all for nanomaterials. Thank you very much for watching. See you in the next video. Assalamualaikum.